Welcome to this presentation on recursion. In programming, a lot of programming languages support a function feature called recursion, and this allows essentially for a function to call itself. And that may sound kind of odd and maybe not clear as to why that might be useful. So let's start out with an example. And this is an example that we've seen before. Here's a program that is really simple. It just defines a string called hello and prints it out. And so if we build and run this, no surprise. What we'd like to do is print the string out in reverse, and there's a few different ways of doing that. One is that we could do a loop where I goes from the size of the string minus 1 down to 0, and print out string sub I. So we're just looping from the end of the string down to 0 and printing out the characters, and that should print out the string in reverse. And we get a error message. That's kind of interesting. Oh, so I've got a bug here where I incremented I. So used to doing a loop with I++. In this case, we want I to go count down. So here we're printing out the string in reverse. Ole, and it's in a column, so we can remove the indel if we want, so that it's on the same line. So here's our hello in reverse, and this is probably the preferred way of doing it. It's probably the most straightforward and preferred way of doing it, but as we've seen, there's at least one other way that we can do this. We've used a stack to reverse things, and so we can create a stack of characters and loop through each character in the string. And we could use a range-based for loop for that and push each character onto the stack. For each character in the string, not each character in the stack. Push that character onto the stack. And then when we're finished putting all the characters onto the stack, because of the nature of insertion and removal of the stack, the last thing that was put in is the first thing that's pulled out. If we just print out the characters in the stack from top to bottom, we'll have the string reversed. So we could say while the character stack is not empty, print out the item at the top of the stack and pop that item off the stack. And so we have one loop that takes every character in the string and pushes it down on the stack. We have another loop that takes every character off the stack and prints it out. And this will also print out the string in reverse. So a stack is a useful thing for changing the order of things, reversing the order of a list. And let's show you a third way of printing out the string in reverse. And before I do that, let me show you a C++, a very common string operation that's in C++ as well, called substring. So most programming languages have capability of manipulating strings. And a very common string manipulation feature is this thing called a substring, where you can take essentially a subset or a sub-region of a string, and extract it out and put it in a new string. And so in C++, this substring function allows you to specify a starting position and an ending, a length or a count of the number of characters. So if you put in a 2 and a 3, then it would start at position 0, 1, 2. So it would start at the third character and try to extract out from the third character 3 more characters, or until the end of the string is reached. And so this is a common function that's available in a lot of different programming environments to do a substring. In C++, it has default arguments. So the position starts at the beginning, and the length defaults to this thing called end position, which is the end of the string. It's a huge number, so it's always going to be the end of the string. So if you were to put in a 1 here and just leave the length off, it would essentially give you a substring that doesn't include the first character. It would give you everything beyond the first character in the string. Alright, so let's keep that in mind as we write this function. I'm going to call it print reverse. And this is going to be a recursive function that takes in a string and prints the string in reverse by calling itself over and over again. And we're going to write a special case that says if the string that's passed in is empty, well, then there's nothing to print out, so we just want to return. Else, I want to print out the first thing in the string, but before I do that, I want to print out everything else in the string in reverse. And I have a function that does that called print reverse. And so I'm going to call this print reverse function, and I need to pass in a string. And the string I want to pass in is everything but the first character. So I'm eventually going to print out the first character, but before I do that, I want to print out all the other characters in the string in reverse. And I'm going to use this function to do that. So I'm going to call print reverse and pass in s.substring with a 1. And so each time I call print reverse, I'm printing out or passing into print reverse a modified version of s, where it's all the characters in the string except for the very first one. It's skipping over s sub 0. And so if I replace the stack version of that with print reverse, I also get the string printed out in reverse. So this is a brief introduction to a recursive function. Now let's take a look at recursion in more detail. What we end up doing in recursion is trying to define a problem in terms of itself, and at each step make it a little more simpler. So in this case, I'm saying print out the string in reverse by printing out everything but the first character in reverse, and then print out the first character. And it's very common in recursion, you almost always have to have it, where you need a stopping case. So if you don't have this stopping case that just returns, you would end up calling print reverse over and over again. You get this infinite recursion. It would cause a stack overflow, and your program would crash. So you have to have a stopping case, and in this case the stopping case is once we've extracted substrings so much that we don't have anything left in the string. We've reached the end of the string. S will be empty. And if that's the case, stop the recursion and just return. Let's look at a diagram of how this works. Here's the function print reverse, and here's the output window. We don't have anything in it. Here's main that defines string as a set of characters hello, and we're calling print reverse and passing in string. So these rectangles here I'm going to stack up are what we call the function call stack. And so the first function that gets called when a program runs is main, and local variables are placed here in the stack, and we're going to call this print reverse, so we're going to get another function call pushed down onto the stack. And this function name is called print reverse, and the string that gets passed into S is everything hello. And our code says if S is empty, return, but S is not empty, so we'll do the else part, and this says to call print reverse with something different. We're going to call print reverse with S dot substring 1. Okay, so then I'm going to get another one of these print reverse boxes on it, on top. So we're calling another version of this print reverse, another instantiation of this print reverse function, but because we passed in everything but the first character, the value here is just LO. And we're not doing the cout yet because we've called a function and we can't do the cout until the function returns. Alright? So in this particular case, LO is not empty. We're going to do the else part, which says call reverse with substring of LO. So we're going to get another version of this placed on the call stack. And this time it's everything but the first character, which is just LLO. It's not empty. We're going to call print reverse again, so we get another version of this. Which gets placed on the call stack. I might run out of room here. And this is going to be just LO. Again, LO is not empty, so we're going to call print reverse again. So I get another version of this placed on the top of the stack, and this is going to be just O. And I'm still running out of room. I can shrink these maybe. So now the string is just O. It's still not empty, so we're going to call another version of this, print reverse. It gets placed on top of the call stack. And this time, everything beyond the first character is an empty string. There's nothing after the O. So here's where we've reached our stopping case. For this particular stack frame, of this version of print reverse, S is empty, so we're just going to return without doing anything. So when you return, that means this stack frame gets popped off the stack. Now we're back here. We've already called the print reverse. The next thing to do is to cout S sub 0. In this version of the stack frame, S sub 0 is the O. So on the output, we get an O. After we've printed out the O, we're done with the else part. We've reached the end of the function, and that caused the function to return, so that stack frame gets popped off the stack. Now we're back here in print reverse, and we've already made the recursive call, so we're ready to see out S sub 0, and S sub 0 is the L. We've reached the end of the function, so this gets popped off the call stack. Here we've done the recursive call, we're ready to see out S sub 0, and in this case S sub 0 is the other L. We've reached the end of this function, we pop that off the call stack. Here we are, we've already done the print reverse recursive call, we're ready to do the see out 0, that gets us the E. That's the last thing to do in this function, so this returns, and this stack frame gets popped off the stack. We're here in the initial call to print reverse, where S is hello. We've already done the recursive call, so we print out S sub 0, which is the H. We're finished with this. We're back in main, completed the call to print reverse, and you see on the output we've got hello printed backwards. So this is how you can trace recursion using these animated rectangles to represent function call stack frames that keep track of the different local variables for each recursive call. So that's a demonstration of how recursive calls work. So there's a couple of other cases we can look at this. One is multiplication. So we can think of multiplication as a series of additions. So 3 times 2 is equal to 2 plus 2 plus 2. Or you can think of it as 2 plus 2 times 2. And then 2 times 2 is 2 plus 1 times 2. And so you can break it down that way. This is how recursive functions are defined. You try to define something in terms of a simpler case of the same thing. Not everything can be easily defined recursively, but some things can, and it can be useful to analyze problems this way. We also have to look at one or more special stopping cases to make sure that the recursion stops. You can't have infinite recursion. Recursion is similar to iteration or looping, but you're looping by making successive function calls, and you have to stop the recursion just like you have to stop the iteration, and so you need to identify those stopping cases. And so it's very common in recursive functions that you have some type of one or more if tests to find those special stopping cases. The recursion has some limitations. One is that we've talked about the limited stack frame. The stacks in the function call stack in programming is generally fairly limited in size. There are ways you can make it larger, but you generally don't want to do this for a couple of reasons. One is if you have a very large number of iterations or very large number of recursive calls, you can overflow that stack memory and cause your program to crash. The other part of it is pushing and popping these stack frames onto the stack can actually be slower, so your programs may not run as efficiently. So most production code, most real world code doesn't use recursion. Instead, if you want to solve a recursive problem, a problem that's naturally recursive, you would do it with iteration and use a stack data structure. But it can be very useful in developing and understanding algorithms if you can define the problem recursively and understand the recursive nature of the problem. We'll look at another example which is pretty common in nature called the Fibonacci series. And it's just a sequence of numbers where the first number in the sequence is always 0, the second number is always 1, and then every number after the second one is the sum of the previous two. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on. So after the first two numbers, everything in the Fibonacci series, or Fibonacci sequence, is the sum of the previous two. So we can define this recursively. You can also look at it as perhaps a tree where the Fibonacci number of 5 is the sum of the third and fourth Fibonacci numbers, and then the third Fibonacci number is the sum of the first and second ones, and the second one is the sum of the 0 and the first one. And so this one is 0 and this one is 1 and this one is 1, and you can add them all together. You can think of it as in a tree form as well. Let's take a look at how we might write the code for a Fibonacci sequence, or a Fibonacci number. So each value in there we might say is an integer. Maybe we call our function Fibonacci, and we pass in an integer n. And we know that if n equals 0, that's one of the special cases, and that's defined, the 0, or the first Fibonacci value in the sequence, is 0. And if n equals 1, the Fibonacci number is 1. Otherwise, we make a recursive call. And actually, we make two recursive calls. We say that the Fibonacci number above the first two is the sum of the two previous Fibonacci numbers. Well, what are the two previous Fibonacci numbers? They are the Fibonacci of n minus 1 and Fibonacci of n minus 2. So those are the two previous Fibonacci numbers. So now we can write a loop that prints out some Fibonacci numbers. Get a series of values here, and you can see that each one in the series is, each one beyond the first two is the sum of the previous two. So 34 is the sum of 21 and 13, and so on. So this is a series of what they call Fibonacci numbers. And again, this is done recursively by breaking the problem down into smaller pieces. So in general, the Fibonacci value of a number n is the sum of the previous two. So I can call that function with the previous two inputs, n minus 1 and n minus 2. And we have special cases where the first one is 0 and the second one is 1. And those are our special stopping cases that will stop the recursion. If we wanted to, we may also do this iteratively. So how could we find a Fibonacci number iteratively using a loop? We know that the Fibonacci series is a sum, and we can loop from 0 to n. And add up the values, and we know that if I is less than or equal to 1, then the sum needs to add in I. So if I is 0, we know the Fibonacci value is 0. If I is 1, we know the Fibonacci value is 1. So in either case, if I is less than or equal to 1, we need to sum up or add 0 or add 1 to the sum, whatever the value of I is. Otherwise, we need to add the previous two Fibonacci values, so we need to store the previous two values. So we need to store, say, fib 1 and fib 2. So it might be easier to do it this way. Because I guess we're not summing up. You don't sum up everything. You just sum up the previous two. So we're going to have, I guess, Fibonacci value like this, and we'll set the actual Fibonacci value to 0 in case the loop doesn't execute at all. So the first one is 0 in case the loop doesn't execute at all. And then we'll set the next one to 1. We'll set the next previous two to 1. So if you look at the Fibonacci series, you see that the first Fibonacci value is 0, and then the next one is 1, and the next one is 1. Yeah, I guess we're not summing up all the values in the list. We're just summing up the previous two. So what we'll do is say that the Fibonacci value is equal to the Fibonacci value of So we've got what we're doing is we're keeping track of, this is the Fibonacci value at I, this is the Fibonacci value at I minus 1, and this is I guess this is actually the Fibonacci value at I minus 2, maybe we should call this one 2 and this one 1, and this is the Fibonacci value at I minus 1, so it's maybe a little bit confusing, but so what we want to do is set this to no, I think I had it better the first place, maybe. So this is so the first one is the Fibonacci value at I, and then this one is the Fibonacci value at I plus 1, and this is the Fibonacci value at I plus 2, so that makes more sense. So the Fibonacci value at I plus 2, once we get beyond the first two, is the sum of the previous two. And the Fibonacci value at I starts out at 0 and then goes to 1, and what we're doing is we're taking the Fibonacci value at each iteration. We're taking the one that we calculated 2 steps ahead and copying it into 1 step ahead, and taking the one from 1 step ahead and copying it into the current one. So we're keeping track of the current one, the one at I plus 1, and the one at I plus 2. And so this is a iterative solution to the Fibonacci value, and we know that initially the first 3 Fibonacci values are 0, 1, and 0 plus 1 is 1 again. So this is an iterative or loop for Fibonacci values. And we can test this out, make sure we get the same thing. see that we ended up getting the same values. One came from recursion and one came from a loop. And so it might be interesting to test the performance, and that's one of the things that you have to do in your work this week, is to test performance of one or more algorithms. So one of the things we want to do to test the performance is we want to try to remove cout, because output to the console, converting a number that's stored as binary internally, converting it to base 10 and then sending it to the console is a little bit slow. So we don't want to convert that. So what we might do is do something a little bit different. What if we computed the sum of 1,000 random Fibonacci numbers? So we could write something like sum equals 0, do a loop for I is 0 to, say, 1,000, and sum plus equals Fibonacci, and call it with some random value, say something in the range of 0 to 10. And in order to get, rand mod 10, a range of values from 0 to 10. In order to make sure we're computing the same Fibonacci number, before we start computing the sum, we want to seed the random number generator with some value and make sure we use the same value. So we want to do this exact same code again. We want to do this code twice. One time we want to do it for Fibonacci that's done recursively, and the other time we want to do it for Fibonacci that's done in a loop. So we want to print out sum of Fibonacci numbers from recursion same thing, the sum of Fibonacci numbers from a loop. And we should get the same sum. The interesting thing might be to determine if one method is particularly slower than the other, which method might give us better performance. Let's see if we can run this code. And I just need an extra return statement in here, I guess, or an extra new line to separate these. So you can see that we're getting the same value, 845 versus 845, and that makes sense because we're seeding the random number generator so that all the 100 random values we get will be the same. So we're getting 100 Fibonacci numbers based off of the same 100 random numbers, so they should be the same values that we're summing up, so we get the same results. But we'd like to test this to see how long does this take to do. And the way we can do that is using the system clock that's in the chrono header file. And we can ask the chrono system clock, what is the time now, and store it in a variable, and ask the chrono system clock, what is the time now at some later time, and store it in another variable, and then we can subtract those two, and the number of seconds is the duration dot count. So it's a little bit not quite as easy to work with, but it's not too bad. So if I go up here and include chrono, and then in here we want to do auto before we start the loop, we want to do, so this is the recursive time, recursive begin time equals chrono system clock now. And then when we're done, we want to get the recursive end time as chrono system clock now. And the difference, the recursive duration, is going to be equal to the end time minus the begin time. And then we can print out the recursion time the duration dot count seconds. And we want to do the same thing for the iterative version, but this is going to be the iterative version. And we want to get the begin time, and then we want to print out the loop or iterative time as the iterative duration count. And you noticed I used the auto keyword quite a bit here. The reason is that the now has a odd data type. It's a chrono system clock time point. And so instead of typing all that in, chrono system clock time point, I just use auto. And the difference between these two, when you compute a difference, it's, well, it's again, I guess it's another time point. Well, no, it's not giving us, let's see if it tells us here. Yeah, so here the data type for the duration is a common type chrono system clock duration. It's pretty complex data type. So the use of this auto keyword saves us from having to look all that up in the documentation and type all that out. So if we run this, what do we see in terms of the time? Do we see much? And what we're getting here is we're getting 0 time. It doesn't take, it takes less than a second to do both of these loops. So what I'd like to do is to increase the number of times we do this. Maybe num fib values equals, we did 100, let's do 1,000, and so we'll replace the 100 with 1,000 Fibonacci values. That's odd. We get a recursion time of 1,001 seconds and this one 1,001 seconds. That seems really odd. It's really odd that 100 took 0 seconds. But as soon as we increased it to 1,000, let's try 500. So that's a really odd time time problem that I'm going to have to figure out. Why would we get so the only other thing I can think of is that there was a slightly different version of this data type where we defined the duration as a chrono duration instead of auto. I wonder if that makes a difference. Let's see. So the recursive was set like that, and the iterative was set like that. So we get a duration as a floating point. Maybe that's what makes the difference. Okay, so all right, so we're still back to a 0 in terms of the time. So even 500 values didn't take hardly any time. So let's try, say, 5,000 values. And now we start to see some difference we start to see where it actually starts to take up some time. And surprisingly, there's no difference between the recursion and the loop time. So normally my expectation is that recursion is slower than iteration. Oh, look at that, I've got a bug here. Here the iterative duration is the recursive end time minus the recursive. So I got a copy-paste bug. We need to do the iterative end time minus the iterative begin time. And here we see a difference where the recursive version is about 6 times slower than the loop or iterative version. And that's kind of what we expect to see, that recursion is generally a little bit slower because it pushes all those items up onto the stack and then pops them off. So we've seen a few different things here today. One is recursion, which is a key element in understanding algorithms, which we'll be studying more in this class. And a lot of algorithms can be easily understood and sometimes implemented using recursion. The other is we've seen that we can often duplicate what we've done recursively in an iterative fashion by using a loop and maybe also a stack. And then the last thing that we saw that's very useful sometimes is to be able to time certain operations. We want to make sure and try to not time input and output operations because they're typically slow. If we just want to time algorithms, we want to run the algorithm many, many times, sometimes thousands of times, to see a difference. And you can't really say, the problem is every machine, every piece of hardware is a little bit different. So you have 2 different processors and you're going to get 2 different times. But on the same machine, if you run 2 different algorithms, you can look at the relative difference between those 2 algorithms and see what the relative performance of those 2 algorithms are. So we've seen recursion and we've seen how to time algorithms. Let me know if you have any questions about this.